Hello everyone, my name is John Popovics. I'm a professor at the University of Illinois in Urbana-Champaign in the United States. And I'm very pleased to be able to participate in this third InfraStar training school, although virtual. I'm still pleased to be able to share what I have developed over the years and learned in my experience about non-destructive testing and evaluation, specifically for the infrastructure, so the built environment. And today, I'll go over quite a number of things. I'll start off with some basic definitions. What do we mean by certain terms? Pose some challenges to this great problem, giving some past experience. And then the rest of the presentation, which is almost all of this long presentation, will be going over selected non-destructive testing techniques and applications. First, we'll deal with those that are appropriate for steel structures, and then next we will cover concrete structures and pavements. Again, individual NDE techniques, what they're based on, how to carry out the measurements, how to interpret the data, and how best to apply. And then in the end, I'll summarize. The first question I would pose is, what exactly is NDT, or NDE, or SHM? Well, my definition is that all of these really mean one thing, and that is that we somehow characterize a material or characterize a structure, whether it's with regard to state of damage or behavior or size or something. And we do this by taking measurements that do not meaningfully damage whatever we are testing. So the example I show here is a radiograph of a pair of human hands. We all understand what this means. This is an image that is able to show the bone structure inside. And we, maybe a doctor can look at this and make an inference whether we have a healthy bone or there is a fracture or some sort of problem. So they make an inference. And when we take this X-ray, we don't do meaningful damage or disruption to the hands. Now, it's not true that we make no disruption. Of course, we make some disruption because we are sending penetrating energy in, and there is some effect, some small effect on the cells. But it's not meaningful. It's not meaningful enough for us to not do it. So you may ask, what's the difference between NDT and NDE and SHM? And for me, by my definition, NDT, NDE, NDI, they all mean the same thing, and we can use those interchangeably. SHM stands for Structural Health Monitoring. And for me, my definition, I admit this is my definition, the difference is in the manner of deployment. If we make these measurements as a temporary measure, we take our equipment to a bridge, we collect data, and then we take the equipment off the bridge at the end to do the analysis. I call that NDT or NDE. But if we collect data from a system that is an embedded integral part of the bridge, or somehow collect data in that way, I call that SHM. So really the only difference is the manner of deployment in my definition, right? It's not everyone's definition, but that's my definition. Because after all, the measurements can be very similar between NDE and SHM. It can be based on vibration or wave propagation. And the analysis can be very similar. The difference is in the deployment. Now, regardless of which one we're talking about, we have a challenge, right? So the challenge is that the best way to get evidence of characteristics, damage state, function, operation, is direct measurements, and sometimes these are destructive. So we need to know if there is cracking inside of a member. The very best way to do it is to excavate or open up that member and look with our eyes or document with a photograph the location of the flaw or the defect. So that's the very best way. It's direct and accurate, and it will convince a non-expert that we have a problem, right? But the problem is that this kind of excavation can damage the material. If we need to drill a hole or excavate, in some cases, this is not tolerable because we would damage the structure or the element beyond repair, right? So it can cause damage to the material, although it's needed. So we can do these, but we must do it, sometimes we cannot do that in a very sensitive structure. And in some cases, we can do them in a few selected locations. So they're damaging, they also take time, and they're expensive, but they are critical because they are direct evidence. Now, non-destructive tests, on the other hand, don't cause meaningful damage, as I mentioned before, and we can collect lots of data without any fear of any limit on damaging the material. And we can collect often very inexpensively and get a large amount of data, but the problem is that these measurements are indirect. We are measuring a phenomenon and we are tying it to the characteristic of interest indirectly. And as a result, these data must be interpreted. Now, some NDE measurements are more direct than others. They are more directly related to the property of interest. But in all cases, there is an indirect mapping and we have to do some interpretation. Some are more direct than others, some are better than others, depending on the situation, right? So I would argue that in any assessment of infrastructure, we need both things. We need destructive tests occasionally to verify and convince ourselves of the larger group of NDE data that we collect everywhere. Now, what are these indirect measurements that we are talking about? Well, they all rely on some sort of phenomenon, and in various set of categories. We have mechanical wave propagation, electromagnetic wave propagation, penetrating radiation, heat diffusion, and so on. Lots of different phenomena. And you can see practical examples of how these phenomena are used. So for instance, mechanical wave propagation, we can think of medical imaging. How do you image an organ or a fetus inside a body? Or penetrating radiation, we all understand what an X-ray radiograph or a CAT scan is, right? These are making use of these phenomena to draw some inference about a material through this indirect relationship. So there are lots of different phenomena, but they each have advantages and disadvantages. They have strong points and weak points. And as we go through for a specific job and a specific material, so as we go through these different methods, I hope you see the strength of one method for a certain case, maybe the weakness of that same method for another case, right? Because they're based on very different types of phenomena. When we want to assess the infrastructure, the ideal, the dream, is to have a method that's very fast so we don't have to shut down operation of the infrastructure, perhaps, that it's accurate. It tells us there is damage here and there is damage here, and that it's inexpensive so that we can apply it. Right now, I think for most infrastructure applications, we cannot achieve with one type of measurement all of these three. Perhaps we can select two of these things and achieve it. It can be fast and accurate, but not inexpensive. Or it can be fast and inexpensive, but not accurate, right? So the challenge that we have as researchers and practitioners in this field is to develop technology that achieves all three, the trifecta, right? We're not there yet. And why is that? Because I would say that the infrastructure assessment poses challenges beyond what we've seen in biomedical engineering and other engineering materials. For one thing, the material is very complicated, it's variable, it's inhomogeneous, and that's normal. That's okay. So here we see an example of the cross-section of a post-tension structure. So we have it in concrete. We have lots of different elements. We have concrete itself, which is highly variable, made up of randomly spaced aggregates. We have a duct inside made of a thin steel wall. We have a grout material inside of that duct, and then we have the steel strands. It's a very complicated, variable structure. And this is a normal structure, not a defect. So we have to be able to look through all this normal variation and find the defect. So the material is complicated, and the size and access is complicated. Normally, infrastructure elements are large. A large volume of material needs to be inspected. And it's not easy sometimes to get access to that material directly, right? They can be large and difficult to reach. These are the challenges that we need to overcome to be able to have fast, accurate, and inexpensive scanning technology. Right? These are the challenges. Okay, with that introduction, now I will go over just very specific NDE methods for, in the first case, structures made of steel or metal, primarily, and I will start from the simplest type of method to a more complicated type of method. Well, the simplest method that works well for metal structures is called liquid penetrant, also called dye penetrant. It's a very simple, fundamental method, low technology, but very functional. It works well. And here's how it works. So we have a structure, and perhaps this structure has a surface breaking crack in it, which I kind of tried to show here. All right? In metal structures, these surface breaking cracks can be very tightly closed, so that by eye, it's actually difficult to see them. It's hard to see this crack. So the idea with liquid penetrant is that we just make the existence of these cracks more obvious to the human eye, that's all, by marking them. Very simple process. First, we clean the structure, and remember this is a metal structure, so it should be quite clean. We apply a liquid, a colored liquid, or in some cases, an ultraviolet liquid. And we let that liquid, through capillary action and gravity, seep into this surface breaking crack. We then clean the structure, leaving the dye of the colored liquid in that surface breaking crack. We then apply a developer which draws the liquid out, and then the existence of that cracked mouth is now visible because of this colored indicator that comes to the surface, and it should be color that humans can see well by eye. So it provides visual indication of this presence of this surface breaking crack. And afterwards, the good action, the proper way to carry it out is to then post-clean the structure, bring the dye out so that for the next time that you inspect it, that the dye will go back in. We don't want to clog up that crack with old dye. So basically we just make invisible cracks visible, but they must be surface breaking cracks. And here you see some examples of making cracks visible. And I think the best example of here's a regular photograph of a clean metal element that has lots of cracks in it, but we can't see them because they're tightly closed and the surface is shiny. But when we apply the dye penetrant, we see all the cracks that are there because the liquid, the red liquid, is seeping to the surface. It can be applied on curved surfaces. It's applying a paint, basically. Or it can be colored, or it can be also ultraviolet in dark conditions, underwater, and so on. We can apply these. So here in summary, and I will have a summary like this for each of the methods, we have very simple equipment. It's just a cleaning element, a penetrant, which is the liquid paint, and a developer, and then the inspector's eyes. Of course, we can also take photographs or video images to document this. This method, although very simple, is very effective. for surface breaking cracks. It can indicate small and tight cracks. It's very rapid, it's very simple to apply. It can be applied on vertical surfaces, curved surfaces, hard to get to places. And we don't have any restriction on the shape of the element. The drawbacks are twofold. One is that we see where the crack is located on the surface, but we don't know how deep that crack is. We don't have any further information about the crack. Is it very deep? Is it shallow? Does it curve? What is its morphology? And so on. And if the crack is inside, a totally internal crack, of course this method doesn't work, or if it's sealed because it's dirty or painted, then it does not work. Also, this method doesn't work well for porous materials. So if concrete, for example, absorbs dye in its pore structure, it will always reveal that color. The color isn't wiped away and you don't see the cracks that are left behind. But this method finds lots of applications. It's excellent at finding fatigue, surface breaking, crack has to come to surface, cracks in steel structures like steel connections, like welds. Excellent method, but somewhat limited. The next level of technology that I'll talk about is ultrasonic inspection. So ultrasound is mechanical waves propagating through a material. Now, before I talk about that, I want to give a very basic reminder to everyone about what a wave is. And a wave is the propagation of a disturbance through a material, a mechanical disturbance in this case. When we talk about electromagnetic waves, we'll be talking about an electrical or magnetic disturbance traveling through the material. But here it's a mechanical disturbance. Imagine atoms interacting, knocking physically with each other and sending that momentum downward. We are not moving mass with the waves. The mass doesn't go anywhere. The atom doesn't go anywhere. It's just moving and sending that disturbance. Now, we typically express waves in harmonic form. So the motion looks like a sinusoid, something like this. So the displacement of the atom or the material can have this kind of periodic shape. And we characterize this kind of harmonic behavior by its period. That's the time required for a single round trip of that harmonic. So we're plotting against time. The inverse of the period is called the frequency, and that's measured in units of hertz, or 1/2. And we can think in terms of human physical interaction with sound. We can understand what this frequency means. It's the pitch of a tone. So a high-pitched tone, the right-hand side of the piano, has high frequency, and a low-pitched tone, the left-hand side of piano, has a low frequency. Right? Now, we assume this fundamental relation for all harmonic waves, and that is that the wavelength is inversely related to the frequency through a constant wave propagation velocity. In the next slide, I'll explain a little bit more about what that means. But frequency, again, is a measure of the inverse of the period, or its time repetition. The wavelength, and that's in units of 1/2. The wavelength is a measure of spatial periodicity of the wave, and that's in units of space, like meter. And so naturally, the velocity, which is the speed at which this disturbance propagates, is in units of meters per second, right? So we have wave velocity is a constant, and it defines this inverse relation for frequency, right? A few other terms. Sometimes we use the term omega, circular frequency. That's just 2 pi times f. And then k is wave number, and that's just the inverse of the wavelength. Okay, so let me try with this visual example to explain more. Imagine that we have a material here, and those black dots are, let's say, the atoms of this material that make up the material. And on the left, we disturb a set of atoms, and that disturbance is propagated. So we see here by this kind of waves that there is some sort of, or wavefront, that there is a motion going to the right. You see that there is an apparent motion of this wavefront. I'm trying to track it with the pointer. That speed at which it is propagating is the wave propagation velocity. But if you look at a single atom, that atom is not traveling anywhere. It's stationary and it's just oscillating back and forth, then sending the disturbance to the right. So if we put a sensor, a motion sensor at the end of this, it would monitor the motion of this atom, and it would look like a sinusoid, a displacement over time that looks like a sinusoid. And based on that, we could figure out its period and its frequency. Now the wavelength, which is the spatial dimension, is this spacing between the wavefronts. So here we kind of get an idea of wavelength, frequency, and velocity, which are related by that fundamental relationship. Now mathematically, for elastic solid, a homogeneous material, we can actually relate this wave velocity to its elastic constants of the material, Young's modulus, in this case Poisson ratio, and its mass density. Because after all, how many atoms are there and how they're bonded together, stiffness and density, will affect how that disturbance travels across, right? So this is a mathematical relation idealized for a perfect material, homogeneous, linearly elastic, so on. Now in this case, I'm showing wave propagation where the wave is propagating to the right, left and right, and the motion that sets up that wave propagation, the oscillation, is also in that same direction. So the direction of the travel and the direction of particle motion are the same. This represents what are called P waves, or longitudinal waves, or compressional waves. They all mean the same thing, right? They all have the same meaning, and that's the wave propagation is in the same direction of the particle motion. But we can, in solids, we can also have wave propagation, which looks like it's moving to the right here. But the particle motion that sets up that disturbance is transverse, right? We can have these in solids. So these kind of waves are called S waves, or transverse waves, or shear waves, or secondary waves. They all mean the same thing. It's just that different fields of science use different terms to mean that same behavior, right? And again, we can relate this velocity of propagation to its elastic constants and density. Now, a key component of shear waves is that because liquids and gases, in theory, cannot transmit shear stress by definition, then we don't have the existence of these waves in true liquids, fluids, and such as liquids and gases, right? And also we can see that we could have two polarization directions. That is, we can have the particles moving up and down and sending to the right, but we can also have the particles moving out, in and out of the board, in and out of the screen, and propagating to the right. So that's why we have what we call polarization direction possibilities, two of them. And that will come up when we talk about electromagnetic wave propagation, right? So for all known solids, the compression wave, also known as the P wave, is the fastest, and the shear wave is next fastest, but it's about 50 to 60% of the speed of the P wave. P wave is fast, shear wave is slower. Okay? Now that we have that basic understanding of waves, how can we use this wave propagation in a non-destructive testing tool? Well, ultrasonic testing, or UT, uses these waves, these mechanical waves, directed in a certain direction, and normally with a fairly high frequency, meaning, and we already know this for a constant velocity, that means a small wavelength, and I will indicate the importance of wavelength. And the reason that these waves are very effective is that these waves show large reflection. A lot of energy comes back when we have an interface between two different kinds of materials, especially a dense material, high density material like steel, and a low density material like air. So when we have this interface between steel, for example, and air, we could have that at a boundary, we could have that at a crack, or in a void situation. Much of that wave energy will come back, will be reflected, right? And when we have a reflection, we see in this diagram here, we send a wave in a certain direction and we look for the return echo. And if the return echo is somehow changed, it comes sooner, we know that there must be something here that's reflecting that energy, and it's probably some sort of airfield defect like a crack or a void. And we express this character in a signal. Typically the output of this transducer, which is the sender and the receiver, it's monitoring that surface motion. How is that surface moving? And how is it moving with respect to time? If the wave comes back sooner, earlier in time, maybe we have a crack. Now, what can we see with this? How big does this crack or defect need to be for the ultrasound to see it? And this brings up the importance of the wavelength. The general rule of thumb is that if the wavelength, if the defect that we're trying to find is the same size or larger than the wavelength that you're using, then you will likely see this defect. But if the defect is very small with regard to the wavelength, then the wave will be blind to that defect, and it will pass through, and the reflection will be very small and we don't see it. So what dimensions are we talking about? Well, for steel, considering its elastic constants and densities, we can figure out the wave velocities of the P wave and the S wave. And for certain frequencies, we can then find the wavelength. And you'll see here that now we're talking about on the order of millimeters in sub-millimeter resolution, just barely sub-millimeter, not micron resolution. Millimeter and just sub-millimeter resolution. Right? So we cannot find very small defects, but we can find reasonably small defects. And we control that for a fixed velocity by changing the frequency of the wave. Higher frequency, smaller wavelength. Now, another characteristic of wave propagation I would like to talk about is reflection. When, as I mentioned, when a wave interacts with a boundary between two materials that are dissimilar, then some of the energy is reflected back and some of the energy is passed through, transmitted. How much comes back? Well, it depends on the difference in the materials. A high acoustic impedance difference, a high mechanical difference would be more reflection, for example, steel and air. But it also depends on the angle at which the wave interacts with that interface, as you see here. So when a wave interacts with an interface between two dissimilar materials, we will have some energy sent through and some energy reflected back. And not only that, when we have this interaction, some of that wave energy will convert to the other mode. So if we come in with a longitudinal wave or a P wave or a compression wave, they're all the same, then the reflection will generate a longitudinal wave, but it will also generate a shear wave. The transmission will, and so will the reflection. That's called mode conversion. Right? What is the angle at which these reflect and transmit? Well, that's controlled by something called Snell's law, and you see Snell's law here. But the bottom line is that as you increase this angle of incidence, you will increase this angle of transmission and this angle of reflection. But the reflection of the shear wave and the compression wave will be different because the velocities of those waves are different. But we can use this characteristic to kind of simplify our life and get rid of some of these mode-converted waves. So for example, if we increase this angle, and therefore we increase this angle, we can increase this angle so that the reflected compression wave is going along the surface. That's called the first critical angle. So we just increase, both of these are increasing, and this basically disappears from the body material, leaving only the shear wave. We can then continue to increase this angle until this, theta 4, increases all the way to the surface. If we increase the incident angle even more, then we have no reflected waves and we have total reflection, right? But we can use this to generate wave modes of interest. But this critical angle concept only exists if the second material, the refracted material, has a higher velocity than the first one. That's the only way it works. Now, how do we use this? Well, here is our transducer sending waves. If we send at an angle to the surface of the steel, let's say, and then this material, this wedge material, has lower velocity than steel, we can select an angle so that we only have shear waves in the body of the material, and we can also control the angle at which those shear waves come out. Right? That's called angle beam inspection. And normally we do that to remove the P wave so that we don't have multiple wave modes bouncing around there, making it harder for us to interpret what's going on. Right? That's the reason. Right? And because of full reflection at the outer surface, we can send energy over long distances skipping through a material. So this is a very effective way to inspect a welded connection between two steel plates. This is an end-connected weld here, and we can send the ultrasound energy looking for defects, looking for reflectors, so that it comes back and we can say, aha, there is a crack there. And because of geometry, we know where that crack is. Now, I talked a little bit about the resolution, the ability, what's the smallest size that we can find of a defect. And I told you it depends on the wavelength, right? Smaller wavelengths can see smaller things. But I want to have a bit more detail on that. We have two kinds of resolution. One is axial resolution. First of all, can you see this defect? And then, do you have any ability to resolve multiple defects, right? So the ability to find and detect the fact that this is not one big defect, but two small defects that are parallel to the beam axis, that's called axial resolution. And the idea with axial resolution is that you need a very short pulse duration. You want the transducer to talk for a very little bit and listen for a long time so that they can hear the reflections coming back. So we need a very short pulse duration. How short? Well, the pulse duration should be shorter than the time it takes to travel between these two defects and come back, right? It should stop talking in that time. So in order to do that, the usual rule of thumb is let's increase the frequency, we have smaller wavelength, and we make sure that this transducer, the speaker, talks for a very short time. That's called a damped signal. So these two. We also need to be able to distinguish between two side-by-side reflectors. Can I tell that these are two different reflectors, or it looks like one big reflector? So this is defects that are spaced perpendicular to the beam. Now, this ability depends on the beam spread or the aperture of the transducer. A laser, we can think of a laser that has a very, very small, tight beam spread. It's very tight aperture, right? The energy is collimated, it's not spreading out, right? And so it has excellent lateral resolution. But ultrasonic transducers don't have that. They have a beam spread which we can characterize by alpha, the angle alpha. And we see here, as a rough approximation for circular transducers, alpha is related to the size of the transducer and the wavelength. right? So to get good lateral resolution like a laser, we need small alpha, and to do that, we need to have a large transducer and increased frequency. So for both cases of resolution, we want to increase the frequency, we want to reduce the wavelength so that we get better axial resolution, better lateral resolution, and better sensitivity to small defects, right? So let's go as high frequency as possible. The problem with that is that we have a limit to how high frequency we can generate. First of all, mechanically with tools, it's not so easy to generate very, very, very high frequency waves, right? We have a limit, a physical limit on that. But more than that, when we increase frequency, we also increase the tendency for this wave energy to dissipate and disappear and not propagate as a ballistic signal going down and back. Rather, it just disperses and disappears from viscous losses and scattering, right? So we have to find this balance. We want to go as high as a frequency as possible to get the resolution we need, but not too high such that we lose our ability to penetrate the material with this ballistic pulse. Now, quickly I'll just go through some of the very basic equipment. So what you see here left is a set of transducers. So each one of these can speak and it can listen. So it's both a talker and a listener. And it listens for, the transducer has a crystal that listens for motion and converts that to an electrical signal. Now, your frequency, your beam spread, your axial resolution damping, it's all totally defined pretty much by the type of transducer that you select. If you want to change frequency, you have to change transducer. If you want to change beam spread and damping, you have to change transducer, right? And that transducer is excited by an electrical box which just sends a pulse and also receives the signal that comes back, right? Through the piezoelectric effect, where strain motion is converted to voltages, and vice versa, right? Now, one critical issue with ultrasound is that you have to have an excellent connection, physical contact between the transducer face transmitting the sound and the material of interest. If we have any air gaps in there at all at that interface, the energy will be reflected back into the transducer because of reflection, and we don't get the energy transmitted. So we have to have some sort of glue or coupling material which allows physical contact and allows the sound to generate. In some cases, we can use water as a good couplant. For instance, put an inspecting material into a tank of water, and with specially designed transducer that can be water resistant, the water acts as the couplant. But this is very important. We have to have very, very good contact and coupling in order to get the energy through, and that can be an issue on a rough surface. So here's an example of how it can be used. So here you see an inspector. He's holding this transducer in his hand, which is an angle beam. It's sending ultrasonic energy in. He's looking at this welded connection of this pipe, and he is just looking at how this wave travels and comes back. And here he's looking at a plot of voltage, that's the output versus time. And he's looking for reflections, right? He said, oh, that reflection is from the back wall of the pipe, but this small reflection here is something I don't expect. It could be a crack, and by taking different measurements, a good inspector will be able to locate and size and characterize that crack. We call this voltage, single voltage versus time signal, an A-scan, right? So this is a very common first order ultrasonic inspection. Very portable, applied here readily in the field, but the inspector has to be able to have the expertise to understand what the signal means and interpret it, right? So in summary, ultrasonic testing has some advantages, disadvantages, and infrastructure application. So it's great because it can find subsurface defects. Remember, dye penetrant can't do that. You only need access to one side to send the energy in and out. You can characterize defects in terms of position and size and so on. And with automated systems and collecting a lot of data, you can generate very nice detailed images which give much more information. But there are some disadvantages. Recall the coupling. We have to be able to attach very well the transducer. So for a very rough surface or a dirty surface, it can be difficult to do to get the energy in. And you need that physical contact, so that's a somewhat slow process. It's not a rapid scan without touching. You have to go and physically touch here, collect data, and then maybe touch at another position. And these data can be difficult to interpret. You need experience. A licensed and experienced inspector has years of experience and understands the physics and can interpret the signal to size it. But this has lots of application, and perhaps the most common application of ultrasound is finding, inspecting welded connections, looking for cracks and voiding. It's very good in a practical way in the field. Now, the next method that I'll talk about, X-ray radiography, penetrating radiation, also can be applied for the same job, looking for welded connection, through welded connections, trying to determine if they are cracked or have some other sort of problem. But the phenomenon is totally different. In this case, we're talking about energy, but at a much higher energy level, so that this energy penetrates the material, right? So we can still kind of use this ideal relationship between wavelength and frequency and velocity. Now, but we're talking about extremely high frequencies and extremely low wavelength, right? So low that this energy can penetrate through the atoms, through the material. This is the resolution we're talking about. And how this energy penetrates through the material, that is, what's the intensity of this energy that penetrates and fully goes through the material, is what we measure. So we can launch this penetrating energy, and here we're talking about X-rays and gamma rays, with some initial intensity. It interacts with the material over some distance x with some absorption coefficient, and we get the resulting output intensity. So we measure intensity of this energy on the far side, and from that we can see that in this kind of negative exponential function, that it's a function of the distance that it travels through the material and this linear absorption coefficient, which fundamentally is based on the atomic density, the spacing between atoms, and the atomic weight of those atoms, right? So we can get some sort of idea of density, mass density changes, and thickness changes. Now, here, intensity should be distinguished from energy. Energy is a very specific thing. It's measured by its frequency, or its energy output. Intensity is how much energy is acting on, how much of this penetrating energy is acting on a surface. So if we monitor these changes in intensity, we can monitor changes in density or thickness, right? Or both. So a couple things to point out. When we have a radiation source here, this intensity, as it propagates through a material and through space, dissipates or drops off pretty quickly, right? As the square of the distance from the source, right? So the source drops off rapidly with an increase in distance, and this is just due to dissipation spreading, and it's separate from other kinds of absorption, right? So we're just talking about going farther away from the source. Imagine when we move farther away from the sun, the intensity of that radiation goes down, right? Now, we can say, oh, that means we want high intensity. Perhaps we want to be as close as we can to the source of this object. But in fact, that's not the case. We have another situation in that we want to be able to define a sharp image of this penetrating radiation, this penetrating intensity. And to do that, we need to have a fairly large separation between the source and the object that we're trying to map, right? So this distance from source to the top of the object is d sub naught, and then the distance from the top of the object is t. We can define this sharpness, how sharp, how defined this image is, and we see from this ratio, we want to minimize this number to have a nice sharp image, and usually we want that number should be less than 0.5. That means kind of the fuzziness or uncertainty in your image. We want that to be low so that we have a sharp image. But to do that, we have to have large d spacing relative to t, right? So we want to be far away from the source, but very close to the detection unit. And the detection unit is usually a radiation detector or a film, right? So far away from the source, close to the object, that's a good image. But as we get far away from the source, the intensity drops quite a bit. Okay? So that's the challenge with X-ray. Now, to get over that, we can expose the material to X-rays for a longer time. That's called the exposure time, right? So we get more in, the intensity is accumulated over time. So we have to emit the radiation and let it shine on the object for a long time in order to get the intensity levels that we need, right? So this exposure is determined by the actual intensity of the material, which we can of the radiation, plus how long that we see it, right? So the exposure is usually controlled by how long and the intensity of the source, and for the case of X-rays, we control that from a tube by controlling its current, right? But we want to get an appropriate image density, that is a nice, high, sufficient amount of intensity passing through so that we get a quality image. That means more intensity, that means longer exposure times, and preferably shorter source, but we also want a sharp image. And I'll show you some examples of what I mean by that. Now, this exposure is essentially means the detected intensity. How much radiation have we detected? Here are some examples of image quality. We want to have, in order to detect a defect, we want to have a good contrast, right? That a color or a shading difference that we see by eye very clearly, aha, the crack is different than the body of the material, or that the thickness is different, right? So here in the center portion, we have a very nice contrast. We can tell the difference between the two thicknesses. The light color means that there has been more absorption within the material because of the interaction with the atoms, and therefore the light color means there's less intensity coming through, and this is more. And we have a very nice sharp image. So we have good contrast, good definition. Here we have good contrast, black and white, but the definition is poor. It's a fuzzy boundary because we did not minimize this number somehow. And then here we have poor contrast but good definition. So with these I'm trying to show that we need to balance somehow in the X-ray, we have to balance the intensity and the contrast and the definition, right? The contrast is controlled primarily by the source parameters, exposure time, and the intensity of the radiation, and then the definition is usually by the geometry of the setup. Now, to make radiographs is rather complicated and has safety risks. There is penetrating radiation, it's hazardous to human health over long exposure, so we have to control that. So we have to set up safety requirements, and that can be very limiting in infrastructure. We select an appropriate radiation source. How big is the sample that you want to inspect? How thick is it? What material is it? And so on. What's its geometry? then we expose that to the radiation at a certain intensity for a certain time, and then we create an image from that. And this image is basically a shadow image. It's showing, think of light shining through and revealing shadows of different thicknesses and different densities within the material, right? And the old-time traditional way is that a high exposure, lots of energy going through, is dark, and low exposure, meaning energy not getting through because it's thicker or denser, it's a light image. But the problem with these is that the depth is not revealed. It's just a compressed shadow. You know there's some sort of hole there, but you don't know where in the thickness that is. You don't get any through thickness. And the other thing is that the orientation of a crack, for example, affects the ability to be detected by X-ray. So when the radiation path is parallel to the crack, it's very effective in finding that crack and indicating it as a change in density. But when the crack is perpendicular to the radiation beam, it's very difficult for X-ray to see that. So X-ray is for cracks is directional dependence. But ultrasound is the same. Ultrasound needs the energy to reflect back. So if this was ultrasound, this would be a good case. We would find the crack because there's lots of surface to reflect back. In ultrasound, we would not readily see this crack because there's very little surface to reflect back. But when we're talking about through thickness intensities, this is more effective because there's more distance through which the intensity can be dissipated or not. Right? So, what are the equipment? Well, to generate this penetrating radiation, you can do it either with a tool, an X-ray tube, or a Röntgen tool, and it generates a continuous spectrum of energy, and you can control the voltage and the amperage to control the energy and the intensity of that. But we can also use natural radioactive isotopes to generate gamma rays. And the intensity and energy of that source is determined by the type of the isotope. And of course, in both cases, the exposure time. How long do you expose this material to the penetrating radiation, right? So two common radioactive isotopes that are used for infrastructure are cobalt-60 and iridium-192. Now, in the case for isotopes, we have to determine the age of that isotope because of the radioactive decay, right? The energy intensity is going down over time. So in order to understand the intensity, we have to know the age of this. Now the question here is, when would you use an isotope source and when would you use an X-ray tube? Well, X-ray tubes need current. They need power, electrical power to operate. These are natural. So if you are going to the field and you don't have ready access to electricity, these kinds of sources are preferable. Also, these tend to have higher energies and higher penetrating ability. Now, to detect the X-rays, we need some way to have some sort of photodetector or film in order to indicate the intensity that comes through with a given exposure time and so on. Now, in previous times we used film, like photographic film. This is the same thing. Film interacts with the photons of light that come through and change color. Well, X-ray films interact with the photons of penetrating radiation and change their color or their darkness, right? But the film has to be on the back side because remember, we're going through thickness. So we have to go through the back side. We need a through thickness penetration. So that is one limit of X-rays that I'll talk about. So let me give you some example of cases where what the defect is and what the radiograph would be. And here we have a weld that has a welded connection between two plates and it has two defects in it, two holes, which is a problem. Looking on the side and looking at the top, you can see it looks like this. If we shine the penetrating X-ray or gamma ray from the top, and then we have the detecting film or the detector plate on the back side, we will measure a shadow image of the energy going through. What would it look like? Well, the image would look something like this. So this is the weld bead, so running along the surface, or in this case, running out of the screen. And this color is more light because it's thicker. The weld is thicker, so there's less penetration. But within the weld, we see these black holes, and these black holes are areas with more penetrating ability and therefore defects. Here's another example of what's called lack of penetration. You see the weld didn't go all the way through, so it's incomplete penetration of that weld. That's a problem. Looking at the top, it looks something like this, so then our radiation image could look something like this. A very clear indicator between here and here that we have a thinner section, so it looks darker, right? And we have other examples like incomplete fusion, like a series of black spots, but they're oriented in a line. So that would be poor fusion at the boundary. So just some examples of what these shadow images look like. So the benefits of these are that we can find internal defects. It creates an image which is easy for us to interpret because it's a shadow image. So humans are able to understand that. It can penetrate most engineering materials. And also the surface condition is not critical. There's no contact needed like in ultrasound where you have to have good contact, clean surface, and so on. The energy is penetrating through, so it's excellent. But what are the drawbacks? Well, again, I mentioned when we have a shadow image, it's all of the data are compressed through the thickness into one image, so we don't have any idea about the depth of the defect, whether it's a void or a crack. As I mentioned, the images are somewhat directionally dependent. It cannot find weld cracks that are perpendicular to the ray path. So if we want to use X-ray, it's best practice to use different radiation directions in order to see these different possibilities. The one huge problem is that you need access to the back side. It's not a one-sided method. Source on one side, detector on the other, measuring the penetration. And then finally, it's a radiation hazard. And because of that, that adds risk, it adds licensing requirements and other kinds of hazards. But still, it has its application. So it's very good for finding internal pores or cracking in welds. It's better for pores because they're round and it's not directionally dependent. And in other civil structures, it can also be used for post-tension duct inspection. Right? So we can think about when we compare, let's say, radiography to penetration, we can think of applications where radiography is superior to liquid penetrant. For example, for an internal defect or a void internal, liquid penetrant doesn't work, but X-ray works. But if, on the other hand, we can think of an application where radiography is inferior to that, and that could be a case where we have a surface breaking crack that immediately diverges away from vertical, and therefore X-ray would have a hard time finding that. Or if we don't have access to both sides, we're looking at a pipe, for example, an functioning tubing system, and we can't stop operation and put a film on the inside of the tube, but we can apply dye penetrant. Okay. Now I will shift topics and I will talk about NDT methods for concrete structures and pavements. Up till this time we've talked about methods for steel structures, for metal structures, and now I will talk about concrete and pavement structures. And the first method, which is, again, I'll start with more simple methods and I'll continue on with more complicated methods. And in this method, this first one is called sounding. And you may know it as chain drag or coin tap. But the idea is very simple. And that is that when you have a large structure, but inside of which there is a defect near the surface, it's possible that by mechanically exciting this object and listening that we can find a difference in tone and say, there's a defect underneath. So tapping, coin tap, chain drag, or sounding. And this is a very primitive method, but it does have standardization in the United States, and I'm sure in other countries elsewhere. How does it work? Well, this kind of detection works when we have a defect which is near the surface, and a defect means a non-solid region within a solid region. So an air-filled void or a water-filled void or a large cracked area within a solid, and that crack is filled with air or water, for example. And if this defect is relatively large and is located near the surface of where you are tapping, then by tapping you can set up a resonance much like a drum head. So when you hit a drum, that thin membrane vibrates and pushes a lot of air, and your ear can hear it. So when we have a thin membrane, a thin solid element, which vibrates because you've excited it and it pushes air, we hear it. It tends to vibrate in flexure, and it vibrates at some characteristic tone, just like a drum has a characteristic tone depending on the size and the tension of that membrane. The size and the thickness and the material of this kind of material membrane will also change its tone. So when we are tapping here, we hear a certain kind of tone, but then when we tap here, we hear a change in the tone. The pitch has changed, the frequency has changed. So when we hear a very high tone and ringy tone, we say that that's solid, and when the tone changes to a much lower frequency and it's louder, then we say, aha, there is some sort of defect underneath here, and we can locate it, right? So I want you to remember this concept of this low frequency vibrational mode, drumhead mode, over a defect. We'll revisit this when we talk about the impact echo method, right? So how does sounding work? It's very simple. We have to somehow excite these vibrations, and we can use a hammer to tap and to listen, as you see here. Another effective way is to take a series of metal links in a chain and just let that move on the surface, and that movement of that tapping of the chain excites these modes, and that kind of chain happens to, that tone happens to match well with what humans can hear with human hearing, and so that's a very effective way to do that. So we just drag and listen, and if we hear something, the inspector marks it and say, aha, there's a problem here, and then, oh, there's a problem here, here the problem ends, and so this region has a defect under it, physically marked, right? So let's think about some advantages and disadvantages of this. Well, the advantages should be obvious. It's very exceedingly simple method. You don't have to be an expert to do it. You don't have to be an expert to interpret it, right? So it's inexpensive, and it's effective for these large concrete surfaces when we have near surface defects. Remember, we have to have these near surface defects for this to work, right? What are the disadvantages? Well, we can determine that there is a defect under here, but that's all we know. We don't know its depth, and we don't know any other characteristics. If the defect is small in size or away from the surface, we're not setting up this drum mode and we don't see it, right? So it's not sensitive far away for defects far away from the surface or for small defects, and it's somewhat subjective. The inspector has to have sufficient hearing and attention to hear a tone and pay attention to do it. So it's somewhat subjective, it's not quantifiable, right? But even with all of these defect discrepancies or problems with the method, it still works for large, works well enough for agencies to use it. So if you want to find areas of near surface defects, a very typical example of which would be corrosion-induced delamination in a bridge deck or pavement, this method works well, it's cheap, it's cost-effective, and you can get reasonably accurate measurements from that. Right? But it is not exceedingly fast. Remember, we have to have an inspector tapping and listening, so we're going at slow walking speed. So this is not an exceptionally fast method. Okay. Next order up in complexity is ultrasonic pulse velocity. So this is a simplified, specific test of ultrasound that works for concrete. Now, in steel, you'll recall that we could have a sender and a receiver, the same unit, send in energy and be quiet and listen for defects, right? And looking for any disruptions or interfaces or differences within the material, right? But that does not work for concrete because concrete itself is a very complicated material. We have aggregate pieces within a matrix. Every one of these interfaces look like a defect, but they are not a defect, right? They are the inherent part of concrete, right? It's an inhomogeneous material at the large scale. It's the same scale as our wavelength. So this pulse echo approach, talk and listen from the same sender, usually doesn't work because every interface of aggregate sends back a signal and we just see a huge mess of reflections and we don't see the defect. So an alternative is to take a cue from radiation measurements. Like, can we just send energy through and measure the very first wave that comes through? In this case, it would be a P wave, because remember, they're the fastest ones, right? And we just measure the time it takes for this wave to get through. That's the P wave velocity. And I'll remind you from theory that we can relate P wave velocity to elastic constants and density for a homogeneous, linearly elastic material. It's mathematically sound, right? And so the thinking was, well, maybe we can measure, we can't measure all of the reflections and find defects, but if we just measure this velocity, that gives us an idea of the elastic constants. And if we know the elastic constants, we can tie it to the quality of the concrete, how strong it is, for example. And we can use this as a measure of concrete quality, or more specifically, the strength capacity of this concrete, because the strength capacity of concrete is a very important design parameter for concrete. Engineers need to know the strength capacity, compressive strength capacity of a concrete in order to ensure their design overall is sufficient. So it's a very important property for civil engineers and structural designers. And the thinking is that, well, we can relate these two, right? So we know that compressive strength is somewhat related to Young's modulus, and Young's modulus is related to velocity somewhat. So can we tie those two and say that we will use measurements of this velocity, wave velocity, of the P wave to measure this strength? And that is something that people are very interested in. So the idea would be like, oh, you have a high velocity, you have high elastic constants, we know that means a high strength, right? Or a low velocity means a low strength. And in general, if you have a very low wave velocity, you know that you probably have a poor concrete. And if you have a very high wave velocity, you probably have a good concrete. But this is not a strong and direct theoretical relationship. There is no natural theoretical relationship between the two. It's completely empirical, right? So you cannot use a velocity measurement and then immediately understand its strength. Cannot be done. But unfortunately, many people do use that. It's inappropriate, should not be done. But this method could be used, just like in radiography and radiation, to find internal defects. The difference now is that we're not looking at the intensity, but we're looking at the time. Remember, all we're doing is measuring time, the time it takes for the wave to travel through. And if this time increases, it's possible that there is something in the way which is either diverting the wave or taking it through a path which has a slow velocity. And when the time increases for a fixed distance, it appears, it's an apparent velocity, that the velocity is going down, right? So we can have if we have a defect or a crack which is perpendicular to the wave direction, we see an apparent loss of velocity. Now the material velocity isn't changing, but the path is changing. It looks like it's slower, right? That's why we call it apparent velocity. But again, with ultrasound, if the crack is perpendicular to the wave propagation direction, there will be little disruption to the wave path, and we will have little to no effect, right? And remember that concrete is composed almost always with steel inside of it. If you have steel which has a higher velocity than concrete, in the case of highly reinforced areas, we can see an apparent increase in the velocity because the waves are traveling along the paths of the steel, and it does not reflect the concrete. So it's quite complicated, this ultrasonic pulse velocity. And what I mean to show with this drawing is that factors that affect strength and factors that affect concrete strength and factors that affect pulse velocity sometimes are aligned and sometimes are not aligned. So what I mean is that there are certain parameters which affect the wave velocity and the strength in the same way, that is, they're parallel, they both increase or they both decrease. But then there are other parameters which have opposing effects, right? The moisture content, aggregate type, proximity of steel, these are all disruptive effects. And what I want to emphasize with this is that this is another reason you cannot use wave velocity absolutely by itself to predict concrete strength. There are too many uncertainties, it's too weak of a relationship. It should not be done. However, within a single structure, you have one structure and you map the velocity, so we probably have the same age, water cement ratio, and potential presence of defects or not. Within a certain structure, then if we see relative changes in velocity, we can say, aha, that is probably a defect inside of there. But only because we can compare the two. So it's useful within a single structure to find relative changes, which may indicate weak zones or defects. But again, I stress, it cannot be used to measure in-place compressive strength, no matter how much structural engineer wants you to give that number, or what other people say that, oh yeah, I can predict the strength. It is not reliable. Now, there are ways to improve that situation through preset calibration testing and curves and a large set of measurements and so on, but in generally should not be done, right? Now, this is generally a through thickness measurement. It's a penetrating measurement. All we care about is the energy that goes through and how long it takes to get through, right? So the most typical configuration is sender on one side, receiver on the other side through what's called an epicenter. The selection of the transducer identifies and defines your frequency, and then this unit simply measures the time it takes to go from point A to point B, the distance. Knowing the distance measures the time, you get your p-wave velocity. And we presume it's p-wave velocity because it's the very first arrival that goes through, and we know that p-waves are the fastest. Now, what frequency to use? We always want to use the highest frequency possible to get the best sensitivity and resolutions and so on. But when we increase frequency, we also increase dissipation, scattering, and loss, right? So we have to use the highest frequency that can actually penetrate through the thickness that we want. So what are the advantages, disadvantages, and application? Well, advantages are, it's really a simple method. You don't have to be an expert to apply it and interpret the results. It penetrates through concrete. If you use low frequencies, we can go through meters of concrete. And when you apply it properly within one single element and you look for differences in velocity, it's reasonably sensitive to voids and cracks that are oriented perpendicular to the sound path. But the problem is that, like any transmission measurement, you don't have any depth of field, and it's not sensitive to parallel cracks. And this need to be on both sides, transmitter on one side, receiver on the other, is a limit. Not all structures, for example pavements, will allow that. And finally, it can be disrupted by lots of things, including moisture content and the presence of reinforcing steel. But nevertheless, it is good in a relative measurement within a single unit to find internal voiding or cracking, or weak zones, or general uniformity of the material. So as a relative measure in one structure, it is quite effective. Now, the next method that I'll talk about is impact echo. And when I was talking about sounding, remember we were tapping and letting this drum head resonate, and then listening for the pitch. I said, remember this for when we talk about impact echo. So I say that because I say my suggestion here is that impact echo is automated, scientific, quantified sounding, right? So instead of just tapping and having an inspector say, oh, that's different, I will mark it. Why can't we tap it as before, and instead of just having an inspector listen for sound, actually measure the motion, the vibration that results, capture that and quantify it in terms of frequency content or other things. So for example, here we have an element and we tap it, and instead of listening, we put a sensor that measures motion, and we measure this wave motion output. We can see here voltage over time. This is the A scan, right? And maybe that will tell us that's how we quantify the sounding. But it turns out that in this time signal, it's difficult because it's so long and ringy, it doesn't have good axial resolution. It's very difficult to see any changes. But if we convert, we map this same time information to the frequency domain, so it's just a mapping of one data to a different language, if you will, which you can reconvert back to the original language. It's just a mapping or a translation. That we remap this information in terms of a frequency spectrum. So now we have an amplitude of the kind of energy over its frequency content rather than over its time. So these two signals represent the same phenomenon. It's the same phenomenon, they're just referring to it in a different language, if you will. So if you imagine if you have a bell and you hit it and it has a tone, you can hear that, oh, that has a certain tone, it's a high pitch. We could represent that principal tone that the bell is emanating as the highest peak in the frequency spectrum. And if we convert that back to time, we could measure the period here and invert it, and they should match, right? So this is a kind of more convenient way to get frequency information about the time signal, right? So if we look at some signals where we tap and we listen and we convert that to frequency domain, so here the x-axis is frequency, we see that we're looking for peaks or tones, resonances, ringing, right? We're listening for ringing. Our ear can't hear it, but the sensor can. And we're looking at maxima and measuring the frequency at which it occurs. That's F, right? So here we have a frequency that's a little bit higher, maybe around 12 kilohertz. Here we have a resonance around 6 or 7 kilohertz, right? The frequency at the peak. Well, it turns out that this frequency at the peak, its principal vibration element, frequency F, is related indirectly to the depth at which that defect resides from the surface. That's H. And that's tied, this kind of inverse relation between frequency and depth is tied between a correction factor beta and the p-wave velocity, right? And this beta correction factor depends on lots of things like material properties a little bit, geometry a lot, right? So we have to understand that. So in the case of a thin element, a slab with one dimension small and other two dimensions large, a good approximation for this beta for most materials is 0.96. But for a shorter slab or a different geometry, the beta is no longer valid, right? It is a correction factor. But what I want you to remember is that we have an inverse relationship between frequency and the depth to the defect. So if we look at this element where we have a solid slab, and remember this is a slab, we have a thin dimension and very large x and y dimension. Thin z, finite z, large x and y, that's a plate or a slab. That's where this method works. So pavements or decks. And here we have a full thickness of 250 millimeters. Here we have a void, the top of which is 200 millimeters. Here we have a large cracked area at 150 millimeters, and here we have the same thing at 25 millimeters. Now remember, there's an inverse relationship between frequency and depth. So if we test at location 1, and this is somewhat localized test, it only tells you what's happening underneath the footprint of the slab, right? So at first, here, we would use that formula and we say, oh, using this formula here, this one, I can predict a frequency and a depth if I know the p-wave velocity and I assume a beta of 0.96, something like that. At 1, I will get a frequency of 7.7 kilohertz. We could also get that same frequency if we measured nearby the edge of this defect. Here, at this location, we would be similar to location 1, but as we get close to this edge, we could still see that, but maybe also see the indication of 1. If we move to 2, now we have a shallower depth. The depth is smaller, right? So we would expect a higher frequency, depending on how that depth is different than H1, right? So we now see this higher frequency. But we also see a lower frequency too, because not only do we see this vibration above the hole, but we see the entire vibration like we would here. And this is a vibration method. And this vibration is a little more compliant because a hole is there, right? Now if we go to point 3, you see, aha, it's now becoming more shallow and we're getting higher frequency. And here we don't see that same kind of leaking full resonant mode anymore because all of the energy is trapped within this membrane here. And of course, if we go to 4, we would get a very high frequency here, 76.8 kilohertz by that formula. But then suddenly, we have a very low frequency, very high amplitude measurement. What is this? Well, this is that drum mode that we listen for in sounding. It has very low frequency, very high amplitude. And you can say, yeah, but you told me that according to that formula, the frequency should be up here. And that's because this formula, which controls these peaks, assumes a full thickness stretch mode of vibration, not a thin membrane drum mode, which is a completely different kind of behavior. So when we do sounding, we cannot get any signal at 1, 2, or 3 because there is no drum mode and there's very little energy coming back for us to hear. But here, now we do have a drum mode. We also have a small stretch mode, which is here, but this drum mode dominates and that's what we hear. So impact echo is able to see all of these defects, whereas sounding is only able to do this one and it doesn't quantify it. Okay, just quickly, how does it work? Well, we have to impact with a hammer or a small impactor somehow. We detect the surface motion with a sensor. We feed it to a computer. It detects the time signal, converts it to frequency domain, and we pick the peaks off. Okay? Now, the problem is that this is an ultrasonic transducer, basically, and it needs very good contact with the surface, right, to allow the energy to transmit up. Is there a way that we can make this more practical by not touching the surface? And I'll go quickly through this, but I've done some work here about using microphones to listen. So now, instead of touching the surface, we have a microphone which is listening to this small motion that leaks up, right? And it works. So now you impact the surface, but now this microphone is above the surface, not touching. We have an array here, and we can move at a constant speed, not fast, but we can listen for those impacts and collect the data. And we can present the data in a different way. Now we're collecting lots of spectra, right? And if we stack them in X and Y, we stack the spectra, and we color code its amplitude, we get a 3D data cube, something like this, where the colors indicate some sort of spectrum, right? But the problem is when you have a 3D data cube, you can't see inside, you only see the exterior surface. But if you tie that to transparency, high amplitude, low transparency, low amplitude, high transparency, then we can see inside of this data cube and we can find the defects. That's an image opacity, right? How does it work? Well, let me just show you. I'll collect scanning data across this, these several defects which are embedded into a pavement, right? And we see that when we stack these 4D images, then we have a nice image which any inspector can say, like, aha, where there's a dark spot, we have some sort of defect. And you see the match here is quite well. We applied it to an active bridge deck, and it worked well. The dark areas indicate near surface delamination, and the cores were indicated by the red dots and the open circles were confirmed. So for the impact echo method, we have advantages, disadvantages, and application. As we see listed here, the advantage, and this is quite a good one, is that we can apply it to the sample from only one side, so it's accessible to pavements and most bridge decks. And now it can be applied to find internal flaws at any depth and get some idea about the depth of that flaw. But there are disadvantages. These spectra, the frequency signals, can be difficult to interpret. It's not really complicated to complicated geometries. Recall that these simple analyses that I showed are applicable to plates, so thin in one dimension, large in the other. When the geometry deviates from that, this method is no longer applicable. And finally, because the frequency is relatively low, the wavelength is large, and thus we are insensitive to small defects. We just can't see them. But nonetheless, this method is quite effective in determining extent and location of defects in pavements and decks, for example, corrosion-induced delamination. And in some cases, it can be used to monitor the quality of post-tensioning tendon duct grouting, although its effectiveness in that case is not as strong. Now, moving to another ultrasonic method, which has a little bit higher complexity value level. Here I'll talk about multi-sensor ultrasonic imaging, or ray imaging with ultrasound. Now, the idea here is that, as I mentioned before, it's difficult to use a single ultrasonic transducer in concrete in this pulse echo format because of the tremendous backscatter from one individual sensor, from all the aggregates, and therefore we don't see the defects. But if we have an array of sensors over a footprint on an area that are acting, can we maybe control them, sequence them, use them together to overcome this problem and affect pulse, echo, or send and receive ultrasonics to concrete? And that's the idea behind this multi-sensor ultrasonic imaging. And so the idea here is, if you look, is that instead of having one sensor, we have an array of sensors. In this case, on the top one, a 4x6 sensor, and and on the bottom one, a 4x12 sensor array set. So each one of these are individual transducers which can send and receive energy. In this case, these are shear wave transducers, so they're generating shear waves in the material, and they're able to do so without, because of this unique design that I'm showing here, they're able to do that without necessarily having any sort of coupling. It's all a strong mechanical contact, right? So the idea is that we send lots of wave energy in different paths, collect all this information, and build back an image to find out about a defect inside. Now, this works despite the fact that we don't use any couplant because of this special transducer, which is called a dry point contact transducer. So we don't need the traditional ultrasonic transducer with oil or grease or glue or something, but rather these individual sensors are in strong physical contact, and they vibrate in a shear fashion, usually around 50 kilohertz, and they're able to, in a very practical way, send and receive lots of ultrasonic energy in a short amount of time. Now, when we generate these waves, we have to remember that the sound field that comes out of it could be a little bit complicated. So in the case here, we see a 4x12 array. Each one of these units is a transducer, and its polarization, that is the direction of its motion, mechanical motion, is transverse here, following that yellow line, right? So when each one of these transducers generates a wave using that shear motion, we see in this 3D representation here that we have somewhat complicated stress field that results. So this is a snapshot of the wave energy. So we generate this nice clean shear wave signal when the polarization direction is this way. So in the direction perpendicular to the polarization direction, we have a nice clean hemispherical shear wave signal that propagates into the body. But in the direction of the polarization, we don't have much shear wave energy at all, and in fact we have a lot of surface wave energy, which I'll talk more about later, what a surface wave is, right? So we have P waves, surface waves, and shear waves. So in some directions it's complicated, in other directions it's clean. So that's just something to remember, that we have sometimes complicated wave modes that are generated. But the idea with these is that we can have these sensors and we can fire them in a certain sequence. We can fire them all at once to get a big energy over a large footprint, thereby replicating a large aperture size and an improved lateral resolution, for example. Or we can phase them in sequence, that is, like firing at 1 and listening at 2 to 10, and then firing at 2 and listening at 3 to 10, and so on. We can generate different kinds of data. And the example I have here is that when we fire at, say, 1 and listen at 0.6, fire at 1 and listen at 6, maybe we get a signal that looks like this at 6, right? And then we fire at 1 and listen at 8, maybe we get a signal like that. So we get some wave components that travel along the surface, but we also get, from that clean shear wave field that I pointed out, we can get a wave that travels inside and reflects back, and that's the reflected shear wave. This is the concept of the pulse echo shear wave, send and receive, look for a reflection from a defect. We're interested in that component. And we collect lots of data, which is, I'm trying to illustrate with this stacked file here. And in those, some of those have these reflected shear wave data. Those are the key, right? Now, once we have these just stacks and stacks of data that I, for example, show here, what can we do with them? Well, we can maybe reconstruct all of these signals using an algorithm to provide a potential cross-section that caused this signal pattern. So we have lots of signals, and we invert that and say, what caused this pattern, that's called inversion, And one method that's used, just one of them, is called SAFT, or Synthetic Aperture Focusing Technique. And in essence, we take a lot of these side-by-side signals, sending at 1, listening at 2, 3, 4, 5, and so on. And we do some manipulations with them. So if we just stack them as they were now, as they are received, and we color-coded them, the amplitude is in color, we may get a B-scan representation like this. But if we take all those time delays and we play games with some shifting and summing and finding superposition, we can try and reconstruct a more realistic cross-section that caused that scattering. And that's the idea with SAF. So a multiple linearly spaced signal shifted in time to superimpose in a coherent way to make sense that provides some sort of cross-section that could give rise to that scattered field. Now, this all sounds complicated, but in the end, what it means is that if we collect data along this top surface, what these kind of reconstruction algorithms should do is give you an idea of the cross-section over which that energy is interacting. So we put the footprint here of all the arrays on the top surface, let them fire. On the left, we have a full thickness slab. On the right, we have a full crack here, deterioration, and it ends right about in the middle, right? So if now we did a series of those ultrasonic data collections with reflected shear waves and the other waves, and we use an algorithm, SAFT for example, to reconstruct what that could look like, we get something like this. This is the reconstruction of that cross-section, which could give rise to something like that. So here it says it's a depth image, so depth and lateral dimension. So it's like this cross-section that we're looking at here. And we see that, aha, there is a thickness for a while of about 8 inches. Sorry, this is in American English units here, about 8 inches. But to the right-hand side, we have a nearby defect, right? So this gives us this cross-section, that representation that we see here. It's a very effective way to tell us what's going on inside. So these kind of multi-array ultrasonics give an image which represents, in most cases, a cross-section that shows the position of any sound reflectors. And we know that wave reflectors are usually interfaces with very different impedance. So that means air-filled holes or air-filled cracks. Now let me just give you an example of we can collect lots of data and do lots of different kinds of inversions to give our images. And let me just give you an example here, which I've taken from this source of researchers from Bonn in Berlin, where they mapped out on this surface of this complicated post-tension concrete beam. They want to find the position of these internal ducts. Now these internal ducts are reflectors, so we should be able to see them, right? So what we can do in this case is do other kinds of complicated imaging. So in this case now, even though we collect data all along this face, we take all of those data, this complicated data, and then we reconstruct the reflectors along a single slice of the cross-section. That's called a C-scan. And we get, at a depth between 20 and 30, which represents this red line, we see the draping of these ducts, right? So we saw a cross-sectional slice. So this multi-array ultrasonic imaging, very effective in providing images that look like cross-sections. Yeah. And those cross-sectional images show the position of reflectors in there. Now, this imaging equipment, which is now commercially available and more coming to the market every year, you may know them from different names like the Axis Mira or the Icon or the Prozac Pundit. And all of these have about the same kind of design, the dry-coupled array transducers. Quite simple to apply, just the footprint is under here, you push it against the surface, push a button and all the data are collected, and you get this cross-sectional image. So very practical, It gives you a very effective way of looking inside of a structure using ultrasound with concrete, which was not available before the invention of these arrays because of this scattering problem when you use a single element. Okay, advantages, disadvantages, applications. So the advantages is that it's a relatively simple to apply test. You can apply it on one side, pulse echo, you don't have to go to the other side. It can be applied to most surfaces without preparation, and it can detect internal reflectors in space and location, and perhaps size, although that's not as clear that we can effectively image the size. So it's presented in a format that's easy to interpret. However, the depth at which you can interrogate into structures with this is somewhat limited, and if you have a heavy layer of steel reinforcement near the surface, that will act to shield all the wave energy. All that wave energy will be reflected and kind of absorbed there. You can't see behind that. Now, because we use a 50 kilohertz wavelength, frequency, the wavelength is relatively large, so we don't find very small defects. And even though this is an array system without coupling, it's a contact measurement and it covers only a footprint. So to cover a very large structure, it would take a long time. However, this is a very nice tool for uncovering, voiding defects or other kind of defects inside of a concrete element. Really very effective for certain jobs like that. Now let me quickly go to the use of surface waves. And so far I've mentioned mechanical waves and that we have P waves or compression waves which travel fast and which are polarized in the direction of propagation, and we have the slower transverse wave or shear waves which propagate transversely to their polarization direction. But we have another wave mode that we should consider, and those are surface waves. These are wave rays that travel, as the name suggests, only along the surface of a solid and air, let's say, or a solid and vacuum. So it's an interface wave, but that interface is between a solid and a free surface, air, right? So to give an idea of what a surface wave cross-section looks like, I've asked you to look at this simulation of a stress field, which is subjected to a point impact here at a certain time. We wait a few microseconds and we take a snapshot of the stress field that results. And what we see is that from an impact event on a solid from air, we have this hemispherical P wave front. It's the fastest one, so it's traveled farther. Behind that, about half as fast, is the hemispherical shear wave front. So the polarizations are different. These are polarized in this way, and these are polarized transversely, also out of the plane. But near the surface, we see that the shear wave hemisphere flattens out, and we have large amplitude, which is indicated by the red color, of energy, and that's the surface wave. It's kind of relegated near the surface, and it propagates along the surface, and it's distinct from the shear wave. It's a little bit slower, about 10% or so slower than the shear wave, so it lags the shear wave behind. So the farther this propagates, we see more of a flattening of this hemisphere, right, as the waves continue to propagate, right? So shear waves only are near the surface, and the wavefront depth is about a wavelength, right? So how deep do the shear waves propagate? About a wavelength in the material, but they propagate from a point of event over long distances along the surface, and they're distinct from the other two wave modes. So the surface wave, how you'd measure them, if you want to measure surface properties, this is a good way to do it. You could impact at one point. You have two receivers on the surface that are measuring the surface wave passing by. And you see that first the surface wave passes this one, and then that sensor, and we have two signals, right? And so we could measure the change of amplitude between those two. We could measure the time delay between those two. And this is a velocity, so the time is related to elastic constants and density. Amplitude loss could be due to energy dissipation and so on. So these kind of fundamental measurements that we could try and relate to the characteristics of the material, either attenuation or velocity. Okay? But this is a rather simple, I'm introducing this concept because it's very simple and to help you understand. But in the case of layered materials or a somewhat finite thickness plate, we have an interaction of the whole surface wave with the entire plate, right? Because the surface wave acts on the order of a wavelength, right? And so if we have some interaction with other materials within that wavelength, we would have a modification to the waves. And one kind of procedure to analyze that and consider the fact that maybe we have a layered structure like a pavement or a damage gradient or something like that is to consider how the velocity of the wave changes with frequency. And the thinking is that, well, if frequency changes, the depth changes. And as the depth changes, we are interrogating different parts of this layered structure, right? So I'm not going to go into detail about this, but you have two sensors and you compare the phase delay of these two at different frequencies, that is the time delay at different frequencies, and you get a plot of the velocity as a function of frequency, right? And now you have some sort of plot which varies with frequency, that means it varies with depth, and you can use an iterative analysis to kind of back compute what is the possible layered structure that gives you this so-called dispersion curve. Now, this is a very numerically intensive approach, and it may converge to an incorrect solution, somewhat limited, right? So a step beyond that is to use not one, but multiple waves. But before I do that, let me talk about the equipment. It's very simple. You have an impact source, wave motion sensors, and some system to collect the data. And there are commercially available units. This one is called the PSPA. And here's the impactor and the two sensors. They collect the data and they do all this digitizing and FFTs and analysis that allows you to get the frequency-dependent surface wave. And therefore try and back calculate what is the structure that gives you that. But as I said, there are some limitations. You only have two receivers. You may converge to an incorrect solution and so on. So another method is called MASW, and that's when you use multiple different source and receiver spacings. You collect a lot more data. And because you have more data, you have a more robust inversion algorithm to back calculate what layered structure or what kind of defects are setting up your dispersion curves here. And I won't go into much more detail, but I'll just point to this reference by Ridin and Lowe that kind of very well describes this approach. Can we use the attenuation, the signal loss of surface waves to find defects? Well, the answer is yes. And I just gave you a little example of some work that my research group has done, is to see how the scatter, the energy lost from surface wave propagation can be used to find defects. Now, because they're surface waves, this is near surface defects within a couple centimeters within the wavelength of propagation. But that is an important region, the covered concrete, where deterioration happens, right? So if we collect lots of surface wave signals over different spacing, we can get a series of surface wave propagation like this. We can stack them in a space-time domain, or TX domain, right? And we see the wavefront here at different times and different spacings from all the signals that we've collected, right? And we get a lot of information there about forward propagating and backward propagating. You see this kind of interesting interference wavefronts. But we can convert this to a frequency wave number domain through a 2D Fourier transform shown here. But the idea is, just like we transformed a time signal to a frequency signal, we can transform a wavelength to a wave number signal. And so we can get a frequency wave number domain from the space-time domain, which is exactly the same, describes the same phenomenon, but a totally different language, right? So we take this time in space image, we do a Fourier transform, we get a frequency wave number image, right? And we used this domain to kind of interpret the signal losses. All right? So to show you kind of a little bit more graphically what I mean is, on the top is a finite element simulation of just concrete. It's a simulation. It shows surface wave propagation. And on the bottom is that same, but now we have distributed surface, correct? So I'll start this simulation, right? And you should see the signal that's a surface wave signal. It's only going into a little bit to the surface. And it's propagating, maintaining its energy. All of these kind of crazy signals you see after here are the signals scatter from the aggregates, right? Because they are a scattering image. But we saw a surface wave propagation. But now, on the bottom, if we see a region that has cracks, let's look at that, and you'll see the interaction is different, right? Suddenly the wave is disrupted, the energy dissipates, and we have these kind of pulsating energy over the cracked region, right? Right? So again, we have a forward and a backward propagating wave, but we have now this kind of scattered region of pulsating energy. And we use that, we did lots of these scans, and we looked for where that energy was pulsating using the FK domain, and we drew maps of cracking damage, right? And so here on different samples that have ASR-induced cracking damage in concrete, we see that the control samples showed very little cracking, and in fact it did, but the reactive samples do show cracking, and where the warm colors indicate regions of high cracking, and that correlated well with other measurements, other direct measurements of damage in the sample. So just an example of how surface waves can be used. So surface waves have some advantages. They're applied from only one surface. That's always good. And you can provide estimates of layer thicknesses using MASW inversion or SASW inversion and general stiffnesses. And as I showed, that you can also kind of infer from the scatter areas of near surface damage. However, this SASW and MASW approach is not very accurate for thickness estimates. It's an inversion. There are some inaccuracies in that. And the SASW method may not converge to the correct solution because of its limited data. But still, the SASW has been used to monitor near surface stiffness properties or thickness and stiffnesses of layered properties, like layered structures like pavements. Can we use it to estimate damage in concrete? Our research shows that it can be quite effective there. Now, another method is completely different kind of wave propagation is radar. That's electromagnetic waves. And the difference here is it's a wave. We can monitor this kind of sinusoidal behavior of the wave propagation. But what we're propagating here is not a physical disturbance, but a disturbance to the magnetic field and the electric field. And this mode only has one possible wave mode. It's a transverse mode. And it's controlled by the electrical properties, such as the dielectric permittivity, the magnetic permeability, and the conductivity. Now, the permittivity shows how bound electrons are distorted in the field. Magnetic permeability shows how a magnetic field produces magnetic flux. And conductivity is related to the electric field, related to the movement of free electrons. So these are all different electric properties, but all of them combine to control the wave propagation. And we see that there are analogous characteristics. We can measure the velocity of that wave propagation, which is a function of the permittivity and the magnetic permeability in what are called lossless dielectrics, that is, the conductivity is 0. And we can also come up with reflection factors. The waves reflect off of different interfaces, but in this case, the interfaces are related to the electrical properties, such as the permittivity and the permeability. But when we have a conductive material, it's no longer lossless, we see that the signal gets attenuated. And that attenuation is essentially a function of the conductivity. The more conductive a material is electrically, the more lossy it will be. As the wave propagates, it loses energy. And that is also a function of frequency. Higher frequencies attenuate more. So we have an issue that this is a wave that can propagate into materials, permeate into materials, but if that material is conductive, anyway, we lose a lot of the energy. And if the material is fully conductive, it's a conductor like a metal, it doesn't really propagate at all in that material. So we can look at some of these characteristics, and these waves can propagate in vacuum. We don't need atoms or mass to do that, and we can look at its characteristics, permittivity and magnetic permeability. And in this case, we don't have any loss because there's no conductivity. And we relate everything to the speed of light. So these are fast-moving waves close to the speed of light. Okay. Now, for most materials that are not ferromagnetic, we can say that its magnetic permeability is close to that of free space, and we only consider the permittivity, the dielectric constant. And we see that the dielectric constant of air and vacuum are essentially the same, so we can call them the same. And we see that they're not too different than that of solid materials, right? Because remember, this isn't a mechanical measure, it's an electrical measure. Right? But the dielectric constant of water is much higher, right? So we can say that air behaves pretty much like vacuum. Water, which is not really a low-loss material because it does conduct electricity, especially with dissolved ions, but it has a high dielectric constant. And concrete, which is a porous material that absorbs water, can have a range of dielectric constant. But all of these are much lower than water and close to that of air. And as a result, we can inject electromagnetic waves from air into solid materials because the dielectric constant is similar, so we have much transmission and relatively little reflection, right? And that reflection is maintained by the difference in this dielectric constants, right? And so they're similar, then they will have relatively low reflection. However, when we have an electrical conductor, and I'm talking about metals here, we have no transmission and no propagation in the metal, and all of the energy is reflected away. So what my point here is that radar is very, very sensitive to the presence of conductors or metals. It will reflect away and cause lots of indication for using a pulse echo kind of format. And that's what we do. In radar, which is sending an electromagnetic pulse and then being quiet and listening, just like an ultrasound, we emit the pulse and we look for reflections. Because of the good transmission between air and solids, we can have a contactless injection of the energy, because a lot of the energy goes through, relatively little is reflected back, and this can penetrate into materials and we can look for reflections at interfaces. And just like we did an ultrasound in a time signal, we look for the presence of these echoes, which indicate some sort of electrical or magnetic interface, right? And if it's a metal, there will be a large amplitude reflection, right? Now here, the velocity is very high, and the frequencies are very high. Now we're talking about hundreds of megahertz to gigahertz. much, much, much higher frequencies. But it doesn't mean the wavelength is very, very small. In fact, the wavelength is generally quite large because the velocity is so large. Remember, they're related to each other by the velocity, right? So the difference between this and traditional ultrasound is that ultrasound, we would have to push the sensor in contact and have good coupling to make sure the energy goes through. We don't need to do that here. That is a great, great benefit of radar. So here you see a typical example. Here's a radar antenna. That's the sender and the receiver. It's on wheels. It can move. It doesn't need to be in direct contact. And we can collect data from scanning, right? And then we collect all the electromagnetic data here. So when we are scanning along the top surface, and there is some sort of reflector inside, let's say it's concrete, we see that if it's air, we get about 45% of the energy coming through. If it's water, we get about over 50% of the energy coming back. But if it's metal, we get 100% of the energy coming back. And we also get what's called a phase change. The sense of the wave changes. So using the amplitude and the sense of the wave, we can determine what our reflector is. But the point I want to make here is that it's less sensitive to the presence of airfield cracks than it is to the presence of metals. Just like in ultrasound, we want to have the battle of frequency. We want to have high enough frequency so that we get good axial and lateral resolution, but the higher the frequency, we get more loss, especially in conductive materials. Right? So we have to fight that battle. So the practical upper limit of inspection in concrete with meaningful depth is about 1 gigahertz, right? And that gives about 16 centimeters of axial resolution. So the wavelength is relatively large. Its resolving ability is not so good in that way. Now, but the great benefit is that we can collect tons of data, right? And by collecting data and just scanning and collecting lots of information from our antenna. And we can stack these time signals and get a cross-sectional image like we saw before with SAFT and the multi-rate ultrasonic imaging. So now we're looking at a cross-section of depth and distance, right? And the color scheme or grayscale scheme indicates the amplitude of the signal that comes back, all right? These parabolic-looking signals are reflections from an individual circular reflector, and then these kind of horizontal indications are from a back wall. Now, to give you a better sense, if we have a concrete structure here, a slab with varying thickness, and a pier underneath it, and we scan along the top and we just stack those images, we get something like this here. We're able to trace the back wall structure and the change in depth of that concrete slab. And all of these indications are from reinforcing bars. And we also see over this section here, we kind of lose the information because it just keeps going through that structure. Now, if you collect a lot of data in an XY coordinate and use reconstruction algorithms like SAFT, you can rebuild a 3D structure of the reflectors. And in this case, we're imaging the rebar because remember, it's very sensitive to the presence of metal, right? So it's a great metal detector. And then we collect a lot of data, invert it, and we can get these beautiful images which give a very good idea of position, location, depth of embedded steel. So advantages, disadvantages, application. Advantages, the main one is that it's contactless, you can scan, you can collect lots of data very quickly, and is super sensitive to embedded metals. So if you're looking for a rapid way to find embedded metals, this is your method to use. The disadvantage is that sometimes the data are a little bit difficult to interpret, and even though it's a very good metal detector, it's not a very good air, field, void, and crack detector. So it may miss, even though large void may exist, because the electrical difference between the void and concrete is small, it doesn't see it. It doesn't reflect back from that. The wavelengths of these are relatively large, so we don't have very good resolution. axial resolution and sensitivity, and sometimes we have difficulty penetrating, especially if we have any sort of moisture inside of there because of the loss of energy at higher frequencies especially. And finally, because all of the energy is reflected from metals, if you have a heavily reinforced structure, all of the electromagnetic energy will reflect off of that, and it's difficult to see what's behind that. Nonetheless, it has great application. It's excellent for locating embedded metals, ducts, rebar, tendon, and so on. And for the case of asphalt pavement layers, it's quite a good method, and it's standardized in the US through this ASTM standard. Now, moving on to another method here, infrared thermography. We'll go pretty quickly. This is where we measure heat flows from a standoff IR camera. Here you see an example where the colors indicate different surface temperatures, right? So the idea is that we're monitoring heat flow through this material, right? And heat flow is disrupted by anything that blocks the heat flow, meaning changes in density. So if we have an air-filled void, that will disrupt heat flow. So for example, if we have heat flow of heat traveling from the bottom to the top, right, that void would block that heat flow, and it would look like the surface was cooler, right, near that air-filled void. So we take a picture and we say, aha, it's colder there. Something is blocking the heat flow underneath. It must be some air-filled void, perhaps. And if water was in that void, that would be less effective in blocking that heat flow because of the higher density and thermal conductivity of water. And therefore, we may see a much more subtle difference in temperature at the surface, or we may see no difference at all. So the key is setting up the heat flow. And the heat flow is driven by a thermal gradient, a difference between top and bottom. But it doesn't matter which direction the heat flows. So for example, if the heat is now flowing downward, this void traps the heat here, and now the surface appears warmer. Right? Earlier, when the heat flow was on the bottom, the surface appeared colder over that defect because it blocked heat flow. But for instance, in the morning, the sun comes out and starts heating an object, and we get a temperature gradient through there, so the heat flow goes down, we will see a hot spot there. So the temperature at the top is greater than the temperature at the bottom. But at the end of the day, when the sun goes down, but the Earth is still maintaining temperature, it reverses the heat flow, and we will see the difference. So the key is a heat flow. We have to have heat flow, otherwise we don't see. So the idea is that this surface temperature, which is trying to measure here, T, is related to what's called the radiance, how it emits heat into the air, right? And so we're measuring with the IR camera this radiance, and using the simple formula we can estimate surface temperature. Emissivity is kind of a characteristic of the surface of how the temperature relates to the radiation. So basically, it can be related to color, light color versus dark color, right? And we can measure that radiation at a distance, right? And then what's beautiful about this is it's a full field image. We take a picture and we get an idea of the heat flow over the entire area where that camera is watching. Now sometimes we need to set up heat flow, so we can, if we want to heat the surface very quickly, we can have lamps or some sort of heat source and flash the surface very quickly, generating downward trending heat flow, and monitor for temperature changes, right, with our IR camera. Here are some examples of active heat flow where we suddenly heat the surface and then the heat flows in, and where there are near surface delaminations, the surface will appear warmer. So you see here an example of this region is much warmer because there is a defect here, and the same thing here. But if the defect is lower away from the surface, that has much lower effect on disrupting heat flow, and therefore we don't see a temperature difference like we see here. This can be applied to infrastructure elements. So basically we let the sun do its job, either heating, sending up a thermal gradient in the morning, or going away in a reverse thermal gradient, and we just take pictures with an IR camera. And here I'll show you an example of a series of photos on a bridge deck delamination in the morning, in the hours after sunrise. So we're looking for hot spots, right, lighter images. And you'll see that these images sort of correlate here with the presence of defects that we have from the bottom determination, which was done separately, right? So this is actually a kind of a corrected image, an extracted binary image of these IR images. And we see where these potential defects are, right? Comparing with impact echo, so IR thermography, we kind of see similar features at different locations, right? So you see that these two can complement each other. Thermography, you have to analyze the data, but it's affected by lots of things. It's affected by the wind. If you have too much wind, you lose the thermal radiance. Shadows, clouds, surface moisture, ground temperature, all of these things can affect IR. So you're at the mercy of the weather and the conditions in a way. You can't necessarily carry out an IR investigation if the wind or the surface moisture doesn't kind of allow you to do that. You're at the mercy of the weather. So, in summary, what are the advantages? Well, it's a rapid method, it's non-contact, full field image, it's beautiful, and it can find near surface delaminations that disrupt heat flow. But it's limited by the environmental conditions. If they're not right, you can't collect the data, especially when you're relying on the sun and the weather. And the depth of the defect is not obtained. You just see that there is a defect underneath. It's probably near the surface, but you don't know the depth, because if it's deeper, you just don't see it. But nonetheless, this method is quite effective for finding near-surface delaminations when the weather conditions permit. It's a standardized method by ASTM. And for bonded fiber-reinforced polymer panels on concrete, which are thin sections, finding regions where they are not well bonded. So the last method, which I'll go through here, is electrical resistivity. And in that method, what we're doing is we're looking for the resistance of flow of electrons to an electric field. The electric field is measured by the potential, the flow is measured by the current, and this ratio in DC is measured as its resistance. How much electric field is needed to push an electric current. And this, we can normalize that to its resistivity, that is, normalize it over the distance which it propagates, and we get units of ohm meter, or the inverse would be Siemens per meter. It's what's called conductivity. So the idea is we push current flows over these equal potential fields. And the idea is that this resistivity can be related to concrete properties. Right? When we have low resistivity or high conductivity, we probably have a porous material with high moisture content and high dissolved ions content. Right? So that indicates concrete that's probably not durable. Right? But the problem is that it's also affected by the moisture content in general and the presence of underlying steel bars. Now, this can be measured in the field relatively easily with this 4-Winter probe element. So we drive the currents on the outside and we measure the potential across. Knowing the distance between there, we measure that resistivity. And that's just a number which tells how easy it is to push current for a given flow. But the depth of the inspection is only on the order of the span of those sensors on the Winter probe. The problem is that concrete shows a really wide range of resistivity values that depend on a lot of things, especially moisture content. So we have to make sure that we have some control or understanding of the effect of moisture content on these resistivity values. But in essence, if we have very high resistivity, then it's likely that we have a low susceptibility to corrosion. And conversely, if we have low resistivity, we have a higher risk of corrosion. And here you see these kind of benchmark numbers, approximate. But again, these are very variable measurements. You have to be careful about that. Can they be used for other applications? Well, we used resistivity to try and characterize steel fiber reinforced concrete. Could we characterize the fiber distribution, fiber placement, and fiber volume? And we did these tests on high-strength concrete with different steel fiber orientations. We took measurements in a circle across different paths, and what we found is that, how these patterns varied indicated the fiber content and the preferred or nominal fiber direction for the most part. And so here you see it's kind of an elliptical behavior of the resistivity over the circular path, and that correlated, if we changed that circumferential measurement to an angle, we see that that correlated very well with the fiber content around that circumference, which we measured visually. So just an example of how you can take these measurements beyond simple corrosion prediction. So resistivity, it's a very simple test, relatively little surface prep, one-sided, and it gives some information about the condition of the material that can be related to the durability, especially related to corrosion, right? But it's a highly variable number. It depends on moisture content. It's only near surface, and it does not directly measure corrosion. It just measures the likelihood, the potential of corrosion, right? So the application is usually normally used to characterize the near surface region of concrete, the so-called covered concrete, to get an alignment with other methods can give you a better idea of the corrosion condition. So, very long presentation. We went over lots of things. In summary, I have just a few points that non-destructive testing can be very useful, essential as an additional test to help inspect infrastructure, but they're indirect measurements, and you have to understand the phenomenon, you have to understand the mapping to the characteristic of interest. Sometimes they're direct and effective mappings, and other times they're indirect and less effective, and you have to understand that, right? But you can overcome these indirect problems with the testing correctly, signal processing, and using multiple sensors, and so on. But you have to understand the phenomenon. Ultimately, no single NDT method is good for every application. If you want to have a good sense of what's going on, you have to use multiple different phenomena, different methods, holistically consider them, perhaps with data fusion, look at the whole picture, and confirm with direct measurement. Thanks very much. Here's my contact information. And next year, I hope to see you in person. Thanks very much.